Three, two, one. Alright, welcome to a fun pre-recorded time. Alright, so last time we talked a little bit more about linear transforms, and today we're going to look at some related ideas with coordinate vectors and the change of coordinates matrix. Alright, so last time we demonstrated that if you've got any linear mapping between Euclidean space, there is a unique m by n matrix A, so that the output of T is simply multiply your input by the matrix A. So every linear mapping is given by matrix multiplication. Alright, so there we see that linear mappings in Euclidean space are pretty restrictive. They have to be matrix multiplication, no other choice. But what's nice about this theorem is that the A is easily constructed. It's simply the output of the mapping at the standard unit vectors. So if you have a linear mapping and you want to create this matrix, you simply just look at the output at your standard basis elements. That'll give you your columns of your matrix. So pretty easy to compute. However, we also demonstrated that if you have any basis for a vector space, then there is a unique linear mapping that sends those basis elements to whatever vectors you like. So if you have any basis, linear mappings can be constructed. So with these two results proven, this leads to a pretty natural question. Suppose that I do have a linear mapping between Euclidean spaces. I've got a linear mapping from Rn to Rm. Right, but based on the previous lemma, I just need to know what it does for some basis, right? Then it's uniquely determined. All right, well, this result says that in order to construct this matrix, I need to know what it does at the standard unit vectors, but this result says that, well, you just need to know what it does at some basis. So let's say I've got my linear mapping and I have its outputs for some basis. How do I actually compute this matrix A? Right. So let's go through the breakdown on how you would actually do that, and that will introduce these two ideas of coordinate vectors and change of coordinates matrices. Alright, so let's suppose we do have a basis for Rn, and for ease of use, let's call it B. So B is the collection of vectors B1 to Bn. Alright, well, as we noted, if you have a basis, then for any element in that vector space, there is a unique set of scalars, alpha 1 to alpha n, so that x is equal to that linear combination of your basis, right? Your basis, so you span, so you're equal to a linear combo, and the linear independence ensures that the scalars done so are unique. And as we already noted, this gives you access to a function, essentially. So given a vector x, then I can create this other vector in Rn where the entries are the scalars you use to form x as a linear combination of your basis elements. Alright, so given any vector x, we can create its coordinate vector by figuring out what these scalars need it to be and just putting them in a vector itself. Alright, so note that if we define this vector like this, if I revisit my equation here, what I have then is a linear combination of these vectors b1 to bn. But as we know, if you have a linear combination of vectors, you really have a matrix multiplication. So if I let P sub b be the n by n matrix whose columns are b1 to bn, then this linear combination here for x is actually this matrix multiplication in disguise. So our vector x is actually equal to a matrix times this coordinate vector for x with respect to the basis b. Alright, so the matrix P sub b will correlate the change of coordinates matrix for b, so note its columns are just b1 to bn. And note that since that's what its columns are, it's got to be linearly independent, and the columns are linearly independent, and thus the matrix is invertible, which then gives us this equation right here. So this reveals that if I have a vector x, and I have a basis b, if I want to actually compute its coordinate vectors, I just multiply the matrix x by the inverse of that matrix b right there. So this actually now gives us an explicit way of computing these scalars for a linear combination. So if you have a basis for Rn, and you have a vector x, and you would like to figure out what these scalars actually need to equal, well, now we actually have an explicit formula for that. The scalars are given by taking the matrix x and multiplying it by the inverse of the matrix whose columns are the basis elements. Yeah, it's pretty cool. All right. Now, equipped with this, we can go ahead and answer our original question. Suppose that I do have a linear mapping from Rn to Rm. I have a basis B for Rn, and I have the matrix B, whose columns are going to be these outputs. So let's say I do know those outputs for these basis. I'll make a matrix by smashing those together. All right. So then, for any element, any integer from 1 to n, if I look at the standard basis element ek, I know it's equal to this linear combination of the change of the basis elements b1 to bn. Here I have my change of my coordinate vector entries. All right, well, t is a linear mapping, so if I apply t here, the scalars pull out and the sums pull apart. And then what do I have here? Well, I've got a linear combination, but note that these are precisely the columns of my matrix B. These are the scalars I'm using, so this has to be this matrix multiplication, but as we noted, this matrix multiplication is actually equal to that. So I can replace the coordinate vector for the standard unit vector with this matrix multiplication, and we can move the parentheses over. And note that this would reveal that the output t of the standard unit vector ek equals this times the standard vector unit vector ek. Now recall this thing right here is the column for the matrix A. And multiplying by the standard unit vector gives you the column. So this means the columns of A, the matrix for the linear mapping T, are precisely the columns of this matrix right there. So in other words, the matrix A that we are looking for is in fact equal to the matrix whose columns are given by the outputs at the basis multiplied by the inverse of the change of coordinates matrix. And there you go. So if you have a linear mapping and you know its output for a basis, if you want to construct its matrix A, then you simply need to take these, create a matrix, compute the inverse of the change of coordinates matrix, and then compute this matrix multiplication. All right, so there we go. So last time we figured out how to do this, but for a nice looking basis. So let's go ahead and give this new equation a spin. All right, so suppose that I have a linear transform from R2 to R2, and I know it sends the vector 2, 1 to negative 6, 7, and it sends the vector 0, negative 3 to 6, negative 12. All right, now I could play around with these and figure out what t has to do to the standard unit vectors, or, as I just demonstrated, I can directly compute the matrix by first making the matrix whose columns are the outputs. So I'll take my negative 6, 7 and my 6, negative 12 and smash them together. I will then take my basis that I was given, create my change of coordinates matrix PB. This matrix is guaranteed to be invertible, so I compute its inverse, which I have right there. It's 1 half 0, 1 6, negative 1/3. And therefore I can now create my matrix A for my linear mapping T by simply computing this matrix multiplication. All right, so I do this matrix times that one, and it cleans up to that. Negative 2, 3 halves, 4. And there you go. There is a way of computing the linear transformation, the matrix for our linear transformation T, even if I was not told what that linear mapping does at the standard unit vectors, I now have this method of computing it. There we go. Pretty cool. All right, and that's all I got for you for today. Quick little video on all this wonderful material. Right, and that covers up everything we're going to need for the exam. We will investigate these things a little bit more deeply when we get back next week from the exam. So that is it for today. I'll see you in person on Thursday.